So when I was writing on the board and I said that it'd be cool if we could give those memory addresses names, when the book talks about declarations, that's what's happening. Yeah, y'all are getting a good lot of use out of this since the screen's off. How about we turn the screen on? So in programs that need variables to be declared before you do them, you do that up near the top of the code. Like you may have something that says, okay, I need a variable named x, and it needs to hold a number. I need another variable named y that needs to hold a number. These are declarations. Python doesn't need declarations. We could do them if we wanted to. We'd just say x equals 0 and y is equal to 0, and that would declare the variable. The textbook always shows declarations up being near the top of the flowchart or the top of the code. We don't really need them in our particular language, but you need to have the idea of them, so maybe sometimes I'll add them to my Python program. For example, if I was going to do that, here's what it would look like. Can't believe I just did what I just did. I did file save as and saved my shell on top of a program. Not what I needed to do at all. I needed to do new file and then do save as. All right. So if I was going to do declarations, we know what this is. We know that we're in Chapter 2. We know that this is Lecture F. So, I don't remember what we started our data off with, like 8 and 9 in that other program. But if these are just pure declarations, all we need to do is set them to 0. And I'm going to add a comment that these are declarations. And then later on, we might want to get our input. So, x equals input, quote, what is the value of x, question mark, space greater than, end quote, in parentheses, right? And then convert that to a number so that we can do something with it. X equals float x. Then I would do the same thing with y, right? In this language, you don't have to do this. In some languages, you do. In some languages, you have to create the variable before you can use them later. And so that's what the declaration step that is shown in the book in all the examples does. I'm not sure I'm going to leave that in here because from now on, every single time I run the program to demonstrate it, it's going to make me type in something, right? And so I may wind up commenting that out. But that's the idea. And then we could input something else into y, and we could add x to y and store back into x, or whatever we wanted to do with it. Whatever we wanted to do with those variables. So like y equals x plus 1. There. Now we did something with both variables. The act of declaring it is supposed to give it a name, and it's supposed to indicate what type of data it can hold. Now in Python, variables are not restricted in the type of the data that they can hold. If you give it an int at first, and then later on you give it a string like that, and then this next line gives it a float, well, that variable changes its form in order to hold any kind of data that's required to. In some languages, once you declare a variable as being able to only hold an integer, that's all it can hold. And so if you tried to do that and store a floating point value in it, that would be a syntax error. Or if you tried to do something like this, which returns a string and stores it into it, that would also be a syntax error. Python's a little bit easier in that respect. So I usually skip the declaration step in the kind of languages where you're allowed to skip the declaration step. Note, prof usually skips the declarations in Python. Now there could be a good reason to put declarations there, and that's if you're going to list what all the variables do, right? Like what is x? Well, I don't know. We're going to say that x equals the number of bluebirds. Blurbirds? Right. And we're going to say that y equals the number of eggs. for whatever purpose, right? Now that we have done this, we can look at the top of our program and see what our variables mean. Now, if I'd given these better variable names, I might not need these comments. But that's about the best reason to have declarations up near the top of your program, is so that you can document what the variables are. So that if you see A, you know that A is supposed to mean age. Now, you should have called your variable age to make the code easier to read. Whoopsie. So if you see M, you know that it means mass. But maybe you should have called the variable mass. But maybe you need to know the units, right? So mass equals 0. We could say that that was in kilograms, right? So mass equals 0, and I might want to put a comment that says mass in kilograms. Or kg is enough, right? There we go. So I'm just explaining. The computer doesn't care whether I add these comments in or not. It doesn't care one bit. These are just for us to understand what the code is doing, so that I can tell the next person, who might be myself or might be another programmer, how the code is working and what it means. It's like scribbling stuff in the margins, except your scribbles in the margins might be a lot more than what's actually in the book, right? Our comments here are longer than these little bitty commands. And comments are pretty important. You can be sure that the people who are programming the computers that were used in the Apollo mission, and supposedly the chips that are in your phone charger, you know, your USB-C phone charger or whatever, are more powerful than the chips that were in the Apollo moon missions, right? But anyways, you can be sure that they were documented extremely clearly so that you could understand exactly what they were doing when you were looking at the code, so that if you made a change, you wouldn't crash the Apollo moon mission. And that sounds a little bit silly, but there have been programming errors that caused complete destruction of space equipment. Like one of the missions that was sent to Mars, right? You know, land a lander on Mars. It had a programming error where, in the past, that module had been expecting input in terms of English units, like pounds and feet and stuff like that. But then somebody rewrote it so that another module was returning things in metric units. And this module hadn't been changed to expect metric data. And so what happened is that lander was sent to orbit Mars, and it orbited perfectly, and then it was time to land it. And so what did it do? It just turned itself towards Mars, fired its engines, and slammed into the planet. And whoops, there goes $8 billion because of a programming mistake. True story, not made up. So here's an example. No. See if I can actually get this to open in a way that we can read it, if it's not too blurry. Yep. Apollo ground control, or whatever, you know, computers that controlled the mission, controlled the equipment, were written in some form of assembler language. What is assembler language? Assembler language is where each opcode has been given a little English name to make it easier to read, right? But you notice that they put an awful lot of comments. Why? Because if all you saw was this stuff without this, it makes absolutely no sense to you. Even this is pretty rough going, right? You know, I don't know what go to E-banks 1, 3, 4, 5, 6, and 7 mean, and I certainly wonder why they skipped 2. But, right, you know, anyways. So, commenting your code is pretty important. And if you work in a programming team, then you're going to be expected to comment your code. And if you don't, then the programmers are going to, other coworkers are going to come hit you with foam rubber mallets. So make sure you do a good job of programming, of doing comments. One common mistake with comments is that people will change the code and then the comments will be wrong because they forgot to change the comments to go with it. So that's what the declarations block is supposed to be. And notice the shape that it's in. I know that we've only looked at flowcharting for 5 seconds a couple weeks ago, but what we saw is that math is done in the regular rectangles, and input and output is done in the tilted rectangles. And I still need to resolve what we're going to flowchart in if Lucidchart is no longer our flowcharting program of choice. All right, so naming your variables. There's all different ways you can name your variables. Remember when I did that mass here? What if I wanted to indicate its units? I could have called it mass underscore kg, right? That would be valid. The book gives that the ridiculous term snake casing, because I guess the underscore looks like a snake. And then you could do it like this, mass kg with a capital K. That's called camel casing, like uppercase and lowercase, but it's camel casing because it's got a hump in the middle. It's got middle, uppercase letters to separate words. Or you can do what's known as Pascal, and I've never seen anybody do this. No, I won't strictly say that's true. That's called Pascal casing for whatever reasons. We're not going to even try to dust off of antiquity. Nobody uses that. I'm going to even delete it. Just know that these are the two preferred mechanisms nowadays. That if you have multiple words in your variable name for clarity, then you could separate them with underscores, or you could separate them like this. This is considered more modern than this. This is considered kind of old fuddy-duddy. However, it's easier for me to for y'all to read and to type, I believe, than if I start mixing in uppercase and lowercase. Why would I want to add kg on it? Is so that later on, far down in my code, if you saw a formula and you were worried that that formula required pounds, right, and then this variable's coming in called mass kg, you might realize, oh, I better write a conversion so that my Mars lander doesn't blow up. So that's what this is showing. Camel casing's got a hump in the middle. You don't just stick a random uppercase letter in it, right? Because if you're tracking somebody's, address, we'd just stick an uppercase D there. I mean, you could. Nothing's stopping you. But, if you have more than one word in your variable name for clarity, patient address, like that, you can do that. Or you could do patient address with an underscore and a lowercase letter. That's called snake casing, like that. Here's one called kebab case, which is even more ludicrous than snake casing. It's when you use hyphens. That doesn't even work in any of the languages I've ever seen. If you put a hyphen in something, it does subtraction in all the languages, so I don't even know why that's there. I'm certainly not going to ask you about that again. Mixed case with underscores. Well, that seems like the worst of both worlds, right? I'm throwing in underscores and I'm capitalizing certain letters. I wouldn't do that. Hungarian notation. This is something that C++ developers, Microsoft developers, used in order to try to hammer in exactly what the variable was and give it its type away in its name. And if I was going to do that, well, if mass is a floating point variable, I might have called it F mass to indicate that it's a floating point variable. And if age is an int, I might have called it IAge to indicate that it's an integer. And if it's a pointer to an integer, I might stick pointer on it. Okay, well, I'm not going to do that. But those are examples of Hungarian notation, and I'm not going to do that in this class because in this class sometimes our data changes type. For example, here it was an integer, x was an integer. We changed it to a string momentarily to hold something the user typed in, and then we converted it to a float. So it'd be absurd for me to try to stick a variable in here to say, oh, that's supposed to be an integer, but then later on, oops, it's now holding a string, and oops, now it's holding a float, and its name is completely invalid. So we're not going to use Hungarian in here anyways, but if you hear that name, it's because you've gone on to do programming in the C++ language where it's common. I'm going to delete those guys. So an assignment statement in pseudocode is where you have the word set, followed by a variable, followed by an equal sign, and then followed by some other expression. And an expression could just be a single number, right? Like if you wanted to store 3 into my answer, or it could be a mathematical thing like that, right? Where you have variables involved and you have numbers involved and stuff like that. So that's what an assignment statement looks like in pseudocode. Some books even go a little bit more overzealous and say that that should be an arrow, right? Well, okay. But anyways, the languages that you're going to learn at this college, none of them use the word set. So I may leave off using set in my pseudocode. It's a superfluous thing, because you know that if you have a variable here and you have an equal sign, that it is doing a set. But the code examples in the book will have the word set, and maybe I'll go with that. But if you leave it off, I'm not going to count you off. So the assignment operator, this is called an operator. Every symbol is an operator. That's an operator, that's an operator. The plus sign's another operator. The equal sign, the single equal, is called assignment. Whereas double equals means I'm comparing two numbers, like if x equals 2. That's checking to see if x equals 2. This is what's known as a binary operator, not because it's all zeros and ones. Everything in a computer is zeros and ones, but because it requires two things. It requires something on one side, and it requires something on the other side. It requires a value and a variable to store it in. Two things, two binary. This is also a binary operator here, because it requires two pieces of data. It requires something to multiply by the other. It wouldn't make sense just to say 3 times and then walk away, right? You've got to know what you're multiplying by 3 for it to make any sense. Now each side of this has got a special term. That's called operand. The operands are the pieces of data that the operator is working on. And then there's something called right associativity or left associativity. And I'm not going to zero in on that. That sounds kind of, I don't know, a little bit too wonky. But right associativity means that the data gets solved on the right first and then copied into the left. Whereas math symbols tend to have left to right associativity, because you do your stuff 2 plus 3 plus 4 plus 5, right? They're being solved left to right, assuming they all have equal precedence. So when you initialize your variable, you declare a starting value. Num, your salary equals 14.55. If I was going to write this in Python and not pseudocode, I would just leave that word off. String, your name equals Juanita. If I was writing this in Python, I wouldn't have a type there, because you don't give them types in Python. And then garbage, that's a variable's unknown value. If you create a variable without giving it a value, which you can't do in this language, but you can in plenty of other languages, if I just did this, x doesn't have a value yet. So it just contains whatever series of bits the computer might feel like was in that memory before it was called x. So it's called garbage, which is why a variable has to be declared before they are used in a value. They have to be declared and have to be given a value before you could use it. If I just said num x and then I said num y equals x plus 1 in a language that supported this syntax, well, how am I going to add 1 to x if it doesn't know what it is, right? X doesn't have a value. It was never given a value. There's no equal sign there. So there's no way that would work unless you came up with a rule for your language that said that everything that was created had a value of 0 until otherwise said. And some languages do that. So variables must be declared before they are used in the program. Like if I give you a program that's supposed to calculate the area of a circle, and I tell you that the equation for the area of a circle is A is equal to, pi r squared, pi times r to the power of 2. That's great. You type that into your code and then you wonder why it doesn't work. Well, the reason it doesn't work is because, well, for one thing, pi is undefined. It would tell us that. And even if we went, oh, okay, fine, I'm going to do that, it's still not going to work because it doesn't know what r is. We have to have an r value before it could even do anything, right? You've got to either ask the user for the radius or at least give it a value, right? If we pretend that the radius is 10, and then we say that that's the area, right? Now it has a chance of working. And for all of our math programs that involve pi, there's a way that you can get a very precise value of pi. You can get Python to give it to you. But it's also totally okay just to use 3.14159, if you can remember that. If you can't remember that, hopefully you remember at least 3.14. It almost sounds like a song. 3.14159. You can go to bed singing that to memorize it. Maybe not. So the variables have to be declared before they can be used, or at least they have to have a value before they can be used. So what is a named constant? A named constant is similar to a variable. Well, it is a variable that can only be assigned a value once. So named constants are indicated by using uppercase letters. So like this pi, I could have made that a named constant, right? I could have said pi equals 3.14159, and then my formula would look like this. The area is equal to pi times r to the power of 2. That makes this code a little bit more readable. This looks more like a formula you'd look up and see in Google, right? If you saw area of circle, it would say pi r squared. It wouldn't say 3.14159 r squared, because really pi is one of those infinite numbers, right? It has no, value that can be fixed in length. It's infinitely long. So this is a named constant. You give a value a name just to make your code easier to read, and also if you want to make the code easy to maintain. What do I mean by that? Well, what if my code is 20 pages long and I do a whole bunch of calculations with the value of pi? Well, what if I keep typing 3.14159 in there and sometimes I make typos? I transpose 2 of the digits, I leave the 5 out one time, and then the customer looks at it and says, no, your results, they are 1% wrong, right? Something like that. Correct your program. We're not going to pay it for you when it's giving us the wrong answers. And so then you go, okay, well, I should have used a more precise value of pi. And so you look up pi to 8 digits rather than 5, right? And so you start going through all your code, trying to find everywhere you use 3.14159, changing it. But unfortunately, sometimes you transpose the digits, and so your search and replace skips those, and it's just a mess. So if you had declared one variable to hold that value, and you stuck that near the top, which is where your declarations really should be, not in the middle of the code, then if you need to change the value of pi to make it more precise, it's easy to fix. You just change it in one place. So that's an example of a named constant. Sales tax, I believe, in Midwest City is 9 1/4. Or if we need to express it as a percentage, right, 0.0925. Just a little parenthetical comment. That way, if I have a whole bunch of calculations, I have a variable which is holding the value, and if I need to change my program, I only have to edit it once. So a magic number, that's an unnamed constant. So yeah, if I'm way down in the guts of my program, and then I do t is equal to, 926.00 times, parentheses, 1 plus 0.0925 in parentheses. And you would look at that and you go, what is going on? Well, this is figuring out the total for the sales tax of a $925 purchase with the Midway City sales tax, right? But it's practically unreadable. These are called magic numbers. Boom, they appear out of nowhere. I don't know what those numbers are, right? Maybe you recognize them. Some numbers are easy to spot. Once you've typed in 3.14159, it'll pop up. But there are lots of other mathematical constants which I don't have memorized, or some that I know and that you don't, or vice versa. If we give the variables names, they're much easier to read. So instead of doing that, we should have a variable called cost, right? Cost equals 925. And then we could say total is equal to cost times, parentheses, 1 plus sales tax in all caps. This makes it real easy to understand what it's doing. This is pretty inexplicable. Now, there's more than one ways to calculate totals and sales tax and stuff like that, but I chose this particular way to make it particularly, the example, right, particularly confounding. Normally what you would probably want to do is to calculate sales tax separately and then add it to the total, right? Because when you look at a receipt, you like to see that it says tax $3.38 and then the total underneath it, whereas this just does it in one fell swoop. So use named constants to hold numbers that should not change during the course of the program. My sales tax should not keep increasing, hopefully. I mean, I guess if somebody passes a law right in the middle, you know, of my program running, maybe the sales tax is supposed to increase, but not really, right? Should not change during the running, during the execution of the program. Use caps, capital letters, right, for their name. That's just not a rule, but it's a guideline that just about all programmers follow. Avoid magic numbers by storing those numbers in variables or constants. And a constant just is a variable. Now, dirty secret is that in Python there's no such thing as a constant. I can't prevent another programmer from going to my code and later on reassigning sales tax to equal the word Bob. Would not be a syntax. But in the languages that do support true constants, then there's a keyword that flags that variable. Don't type this because it doesn't work in Python. It says, by the way, this variable is a constant. And if anything further on in the code tries to give it another value, then it's going to flag it as a syntax error and not run. Which is a good thing. It kind of saves yourself. I kind of wish that the inventor of Python had saw fit to include a constant keyword like a lot of other languages do. But we're just going to make a gentleman and gentlewomen's agreement amongst ourselves that if we see something in all uppercase, it means it's a constant, right? We're just going to agree to that, which is why you saw me do pi as caps here. For those of y'all who care enough to memorize this, if you want the value of pi to like about 16 digits, here's how you get it. You have to add the import statement, but what we're going to do is say from math import pi, and then you can use it. A is equal to pi times r to the power of 2, right? That makes it look a little bit more real. If you feel like it, you can do that. Let's make sure I haven't put a syntax error because I'm always confused about why they didn't make that uppercase pi, and maybe they did. So let's run it and make sure I didn't goof. Okay, yeah, so that worked. If you want pi to a very precise value, you can do that. How precise? Let's print it out, just for funsies. Right, whole bunch of digits. That's like 16 digits of precision. I'm not going to count them individually. It's about what it is. Okay, fine, I'm curious. I'm going to count them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Yeah, 15 places, or 16 if you count that. So if you want a precise value of pi, you can import the value into your program. Or just use, in this class, 3.14159 whenever you feel like it, right? Because it's still pretty much early days for us to be talking about what from means and what import means. But if you can log that into your head and use it successfully in your program, great. But if you can't, just do what we did up here. We declared a variable called pi, didn't we? Right? That works. Or heck, just type it straight into the program. It's throwing a magic number into the program, but I'm not going to count you off for doing it that way. So a magic number is also called an unnamed constant. It's a value that doesn't have a name. Here, I had that. Doesn't have a name, right? It's just a number. Here, It's even worse, right? It appears in the middle of an equation. It doesn't have a name. So these are also known as literals. A number, a value without a name is called a literal, and it's something that's literally typed into the program, and if you needed to change it, the user couldn't change it, you'd have to edit your program to change it for them. So in this case, that's a literal, that's a literal, that's a literal. All of these numbers are actually literals. And then there are another kind of literal called a string literal. See, that variable doesn't have a name. It's just a series of characters. But you could store data into a variable like this. My name is Bob. And then you could print that out. Right? Or I could have just printed Bob like this, right? Two different ways. Well, that's a literal. That's a literal, but in this case, we're storing that literal value into a variable so that we can print it out and use it. And I would rather do that most of the time, but for things like input statements, it's real seductively easy just to go ahead and put the quotes and put the message right there. But then later on, if you were going to translate your program into Spanish, right, then you have to do a whole bunch of searching and replacing, but that ways to get around that and to program defensively in order to be able to do stuff like that are way beyond where we are. We all doing good. Have I given y'all syntax errors yet? Got to try harder. So instead of using 0.06, create a variable called sales tax amount and store 0.06 into it so that the equation looks a lot better, like that. So, arithmetic, we know what all these do. We've been doing, addition and subtraction since the first grade, or maybe they teach it to like 3-year-olds now, whatever. We know what slash means. That means division. The book may try to explain that if you divide a whole number by a whole number, the result is a whole number, and in languages in which that is true, then 5 divided by 2 is not 2.5. Ought to be right. But if a whole number divided by a whole number gives you a whole number like it does in some languages, then 0.5 wouldn't work because that's not a whole number. So what it does is it rounds it down, which would be a real drag because like the equation for the surface, the volume of a sphere is 4/3 pi r cubed. Well, 4 divided by 3, rounded down, is just 1. And so that would mess your formula up completely. Thankfully, we don't have to worry about that in Python. So even if the book mentions integers divided by integers equal an integer, don't sweat it. We don't have to worry about that in this language. 5 divided by 2 really is 2.5. But we do need to worry about the rules of precedence, the order of operations. Rules of precedence are just the order in which math is done. If I have this equation down here, a equals 2 plus 3 times 4, I need to know, and the computer needs to know what needs to happen first. If I just think that math is done all left to right, like if you had one of those little inexpensive, $5 calculators and you had to type in 2 plus 3, and then as soon as you hit the times button, it went ahead and did that multiplication, right? If it's doing it like that, then the answer would be 2 plus 3 is 5. Times 4 is 20. But if you buy a more expensive calculator, your TI-30 or the $100 calculator you bought for physics and only used twice, then if you type in 2 plus 3 times 4 and then hit the equal button, it's going to solve it according to mathematical operator precedence, which means multiplications happen before addition. So what's it going to do? The computer looks at this expression, the compiler does, and says 3 times 4, okay, that's going to have to be done first. And 3 times 4 is 12. And then it's going to add 2 to that. So the answer would be 14 and not 20. And that's the correct answer. We need to know that the computer knows that because we need to know how to program in case that's not what we wanted. What if I really did want to multiply 2? What if I really did want 2 plus 3 to be done first? What would I do? How would I change that? On your calculator, you use parentheses to force something to happen first. So if we put parentheses around that, then it changes the order of precedence. It makes this part happen first. This is sounding familiar like I've mentioned it before, but the orders of precedence, or operator precedence, that's a fancy name. What does this call it? Order of operation. Okay, rules of precedence, orders of operation, anyways. So let's just say order of operator precedence. They came up with PEMDAS, came up with a mnemonic for it. I didn't make this up. Please excuse my dear Aunt Sally. And what does that mean? That parentheses are at the top of the heap. And then exponent, right? So that's the P. Exponent, that's the E. And then multiplication and division. Also, modulus is considered a form of multiplication and division. So that's the M and the D, and then addition and subtraction. And that's the A and the S. And we're at the same level of importance. You just do them left to right. Yeah. It's not like all the additions have to be done before all the subtractions just because A comes before S. The way you think of it is it's kind of broken up like this. P.E.MD.AS, all right? P is the top of the heap, E is the next. These guys are equal in order, and then these guys are equal in order. So if you had an expression like this, A equals 2 plus 3 minus 4 plus 5 minus 6 minus 7, you don't go through here and go, oh, well, I better do all the additions first because A came before S. You don't go, okay, 5, and that's a 9, and no. It wouldn't work if you did it like that. If it was all the same, if it was all additions, then great. But instead, if you're at one level of priority, then they're done just left to right, just like we would normally think of it. So they're just done left to right inside a category. But if you have more than one category involved, then the higher ones are done first. So if I had this 2 plus 3 times 4 plus 5 to the power of 2, if we look at it, according to PEMDAS, what's the very first thing we're going to do? Well, there are no parentheses, right? But are there any exponents? Yes. Yeah, so that'd be the first thing that the computer would do, is it would change that to a 25. Then what? Well, once all the exponents are handled and that's been changed to a 25, it would look for multiplications and divisions, and it would find one, right? So 3 times 4 is 12, and so now we have 12 plus 25 involved here. And then lastly, now that there are no multiplications, no parentheses, no exponents, it goes through and it does all the additions and subtractions. Using parentheses is a really important thing. And sorry for the guys watching the video, but I'm going to write on the board. If you had this expression, A equals X plus 1 over Y plus 2, and I was going to type that in. I'm just going to make it a comment because we don't have A and it's an X and Y is defined. This would not work. A equals X plus 1 divided by Y plus 2. Why? Because all that's going to do is take 1 and divide it by Y and then add that to the rest of them, which is not what I wrote on the board at all. So I'm going to have to group them together with the parentheses to force the order of operation to be done how I want them. And y'all get that right. I mean, you've taken math classes before in the distant past, if not now. There we go. That makes it look like what's on the board. Here's another example. If I Google up the interest calculation, annual interest formula, it's got this to the power of nt. Well, what if I was trying to write to the power of nt in my formula? What if I wanted to do something like, a is equal to x to the power of n times t? Well, that's not cool. Why? Because what's it going to do first? It's going to do the exponent first. And then and only then is it going to do that multiplying the whole thing by t. But that's not what we saw at all. What we saw is everything being raised to the power of nt, meaning that that has to be done before the exponent. We have to change the order in which things are done, and the way you do that is with parentheses. Now that would work. So that's x to the power of n times t. The way we had it written before, x star star n star t was x to the power of n times t. Multiply the whole thing by t, which is not what we want. Like that. So mathematical is done left to right. So is addition, multiplication and division are done left to right. Addition and subtraction are done left to right. It's called left to right associativity.
Oh no, this looks scary.
We haven't even done the first one yet.
Yeah. So this is the page that's telling us that if you divide an integer by an integer, you get a whole number, which is like if you divide 5 by 2, instead of getting 2.5, you just get 2. Not sure in this language. It's worth knowing in the future, but when you take a class on that language, the prof will hammer that in. The book will mention that again very strongly. The remainder operator contains the modulo operator, the modulus. It contains the remainder of the division. Now, what if you want to do that? What if you want to divide 5 by 2 and get 2? Well, there's a separate operator for that. If I do this, x equals 5 divided by 2, and then I do y equals 5 / 2. This is called floor division. It means divide and round down. Not just divide and round. Like if the answer was 2.9, it wouldn't round it to 3. It means divide and round down. Some textbook I saw said that / was had a different name other than floor division. I don't recall. So what's this going to equal? 5 divided by 2 is 2.5. 5 divided by 2 rounded down is just 2. What was left over when we divided by 2 and rounded down? Well, 2 goes into 5 2 times with the remainder of 1. So if we have 5 modulus 2, that means 2 goes into 5 however many times, and 1 is left over. 2 goes into, I love that phrasing, into 5 2 times with a remainder of 1. How about 6, right? If we do 6 modulus 2. 2 goes into 6 3 times, and is there a remainder when 2 goes into 6? Who's awake and can remember the last thing I said and answer the question? Yeah.
The remainder, so 1.
Yeah, there's no remainder when 2 goes into 6, right? Because it goes evenly. 6 is an even number. So 2 goes into 6 3 times with a remainder of 0, right? So 2 goes into 6 3 times with a remainder of 0. And I'm going to stop typing out this long sentence now after that. So if we do this, print 10 modulus 4. 4 goes into 10 2 times with a remainder of what? And y'all know what I mean by remainder, right? If 4 goes into 10 2 times, like that.
Is it giving you a fraction essentially, and it's just saying what the remainder is?
Yeah, except it's not a fraction, right? But if we're doing this long division thing, 4 goes into 10 2 times, and then 2 times 4 is 8. And what was the remainder? 2. And so if you needed to keep doing the division, then you drop a 0 down there and keep going. But that's the remainder, right? That 2. So this is going to print out 2. What about if we print 11 modulus 4? Well, 4 goes into 11 the same number of times. It goes in 2 times, but it has a remainder of 3, right? Because 4 plus 4 is 8. 11 minus 8 is 3. So that's a remainder of 3. And then print 12 modulus 4. Well, 4 goes into 12 how many times? 3. But is there a remainder? Is there anything left over when 4 goes into 12?
Nope.
Nope. So that's back to 0. That's what modulus does. Modulus just means remainder. Modulus does the division and returns the remainder. And what's a use for modulus? Well, there's more than one use for modulus, but I'm going to demonstrate a pretty simple use for modulus. What if you have a certain number of pennies and you want to exchange them for quarters? And so I bring in 128 pennies and try to turn them into quarters. Well, how many quarters will 128 pennies buy me? 5. But there's going to be something left over. And that's the remainder. And when you hear something left over, remainder, that's when you can use modulus. So let's say that I had 128 pennies and I wanted to get the number of quarters. Quarters equals 128 divided by, floor division by 25. Why? Because I want to divide round down. You didn't get 5.3 quarters back, right? The guy who's giving you the changes and going to pull out the wire cutters and snip off, a third of the quarter. You want a whole number. And then to calculate the number of cents left over, it's 128 modulus 25. And we could print that out. We could print out the number of pennies and the number of quarters and the number of cents. So print pennies, comma, quote, pennies makes, end quote, comma, quarters, comma, quote, quarters. I'm sorry this is a long print statement, but you'll see what it looks like when it runs. And, end quote, comma, cents, comma, quote, cents. Part of this is the string that we want to display, and part of this is the data that we want to display. And we're separating everything by commas, which is going to add spaces between everything. So this is going to be the number of pennies, which is 128. That's going to be filled in by the number of quarters, which is 5, we said. And then there was a remainder of 3 left over. Let's make sure that works. Yeah, whatever. So 128 pennies makes 5 quarters and 0 cents. I goofed. My formula didn't work.
You put in 125 instead of 128.
Yeah, you're right. I typed that wrong. And as a matter of fact, why did I type in 125 and 1? This is a perfect example of magic numbers. I should have used the word pennies here. Thank you for spotting that. I was about to get quite confused. There we go. Right? So quarters is equal to the number of pennies, floor divided by 25, and cents is equal to the number of pennies, modulus 25. Same thing. What if you have a football field that's not 300 feet long? For some reason it's 400 feet long, and we want to find out how many yards and feet that is. So yards is equal to 400. No, excuse me. The feet is equal to 400. We have our football field that's 400 feet long. We want to find out how many yards it is. Well, there's 3 yards to a foot. So yards equals feet floor divided by 3. And then the feet that are left over, feet equals the whole word feet. FT equals the whole word feet modulus. I typed modulus and I said modulus while typing // that's incorrect. FT equals feet percent sign 3, modulus 3. Now why did I change that up? I could have just said feet equals feet modulus 3, but that would have erased the original value. Just like up here, I could have said pennies equals pennies modulus 25, but then I would no longer know what I started off with, just for the print statement. So print original feet, how about feet equals, end quote, comma, feet, in parentheses, print makes, end quote, comma, yards, comma, quote, yards, end quote, print, parentheses, quote, and, end quote, comma, ft, comma, quote, feet, end quote, in parentheses. It's going to display the same information as this one did up here. Except it's going to be broken out into several lines. So honestly, I'm going to like this one better. And I'm not sure that I like the way that I worded this at all. When I run it, I may become so horrified I feel like editing it and changing it. Right, so feet equals 400 makes 133 yards and 1 feet. See, why did I say feet equals 400? I'm going to reword that. I'm going to make that say print, parentheses, feet, comma, quote, feet. And how about just one more change? I'm going to remove that word makes from there. So it no longer says print, parentheses, quote, makes. It's just going to say print yards, comma, quote, yards. And I'm going to add that word makes up here. And I think that's going to make about the best possible output we could do while splitting into 3 possible lines. Right? So 400 feet makes 133 yards and 1 feet. Okay, yeah, we could put an if statement in there so that if there's only 1 foot, it prints foot rather than feet, but whatever. How about 1,000 feet? How many yards is in 1,000 feet? Getting real tired of having to answer what the question of x is. Anyways, 1,000 feet is 333 yards and 1 foot. How about 999 pennies? Modify my code. See, we should make the program actually input these things. Ask the user how many pennies there are. Ask the user how many feet the football field is. Okay, so 999 pennies makes 39 quarters and 24 cents. I really do like that format better. So maybe you agree, so maybe it would be worth you figuring out how to express it like that. However, I'm not going to give you a homework where you have to do this kind of conversion yet. We already had a homework assignment this week. I think I'm going to leave it at 1. All right, why don't we stop? Let me make the Dropbox, and then I'll walk around for anybody who has syntax errors and needs help.